Good morning, guys. Starting our first day of online learning. This should be a blast with this class. So the last section we went over was Unit 4, Section B, Lesson 2. The last thing we did was our crossword puzzle on the terms. So the first thing you're going to need to turn in to me, take a picture of after you do it in your books, is the Adjusting for Lift assignment. And remember, all of the PowerPoints are available on Canvas, so you can just go back and click on them to review them to answer the questions if you don't remember. So that's going to be one of the first things you need to do and turn in to me. I'll have a link for it for you to turn in below this video, more than likely. So make sure you get that done. If you're unsure about anything, shoot me an email. And all the papers that we haven't done in our big packet book thing in front of, from all the previous units that we skipped, you guys can pitch those so it's easy to, kind of keep track of where we're at now. All right, so let's go ahead and get started on today's discussion. So today we're actually going to be talking about, some math behind actually calculating lift. So we're going to be looking at the actual equations. We're explaining how pilots compensate for varying lift and changing conditions, and explain the interdependent nature of lift factors for an aircraft in flight. We're going to skip that. So, what is lift? You guys can read all that on your own, right? So I just want to remind you guys that lift is a force that, by definition, acts perpendicular to the relative wind or the line of flight. Lift is what pulls an airplane up into the sky. Lift is created by the shape of the wings on the airplane or the blades of the helicopter. Remember, we've been talking about airfoils a lot lately. So we learned about the 5 factors that affect lift by an airfoil in the previous lesson. So hopefully you're already running through those in your brain, but if you forgot them, let's go over them. The angle of attack, so adjusting the pitch of the aircraft, the angle of attack. Airspeed, by adjusting the thrust or by climbing or descending, I guess would be the best way to put it. Camber, so adjusting the flap settings. Now, the other 2 were air density and wing area, and that's something that we can't control. But the other 3, we have the ability to adjust those things to fly better, safer, and not go boom. All right. So, I guess we're just going to talk about, why do we need to learn this lift equation? Again, we should know all about what it takes to fly, and not just how to get a plane in the air and bring it back down. Because you never know what you might need to know. So, again, pilots, they need to understand all the factors that affect the performance of an aircraft they are flying in order to know its safe operating limits. Recently we saw all over the news about a horrible helicopter crash because somebody flew in a situation that was not safe. So, rest in peace, Kobe. So it's important that we know which lift factors can be controlled by us and which are out of our control. This is, essential for safe flight. Look at that fun equation. So this is how lift can be measured with our formula. Looks pretty scary, like there's a lot of stuff in there, but we're just going to go over all these different variables. So C sub L is the coefficient of lift. It is determined by the shape of the airfoil, a cross-section of the aircraft's wing, and the angle of attack. Differently shaped wings have different coefficients of lift for a given angle of attack. So, little guy looks like a P, let's call him P, stands for the air density. which is determined by air temperature and elevation. V is the velocity of the airflow over the wing. So faster moving airflow obviously is going to generate more lift. S stands for the surface area of the wings. So for small aircraft, the surface area of the wing remains relatively constant. On more advanced aircraft, the wing's surface area can be increased with special lift devices like flaps on the trailing edge and slats on the leading edge. In particular, we need to emphasize that the coefficient of lift is a factor that remains constant unless the angle of attack is changed. The coefficient of lift is determined through rigorous aerodynamic testing and is unique to each different shape of wing. So just look at this formula, and which ones do you guys think have the greatest effects on lift? Sorry, I keep getting distracted. My daughter's in here jumping up and down while I'm making this video. It's distracting me. Alright, so hopefully you looked at this equation and you said, oh, it's probably the velocity, because the velocity is squared. So as the aircraft's airspeed increases, lift increases by the square of the speed. Every other factor in the lift equation is linear. I'm going to have to pause this so I can deal with the kid jumping up and down. Sorry. Alright, I'm back. So, let's talk about the coefficient of lift. So, this is determined by the shape of the airfoil, which generates a set amount of lift. So, prior to a stall, the coefficient of lift increases. So the coefficient of lift is a dimensionless number that is not measured in units like pounds or square feet. The coefficient of lift for a given airfoil shape is determined through the testing like we talked about earlier and computer simulations. Alright, so the shape of the airfoil is the determining factor in how much lift the wing creates. Makes sense, right? So, sorry, I keep getting distracted because we have a Skype meeting and everything keeps going off. So remember that the airfoil is shaped so that the upper and lower surfaces are typically identical, for the symmetrical ones. So asymmetrical airfoils are curved differently on the top and bottom, which we had talked about last week. So a thick airfoil typically will generate more lift than a thin airfoil. If two wings have the same shape but different thickness, the thicker one will generate more lift. So it will have a greater coefficient of lift. Hopefully those noises aren't distracting you guys like they're distracting me. So we can look at those graphs and you can see the difference between a thick, asymmetrical, cambered is what we called it, and airfoil creates much more lift than the thin, symmetrical. So. Alright, so the angle of attack obviously is going to affect lift. Alright, so I'm back. So we need to talk about the angle of attack. It obviously matters. So I'm just going to kind of go through the basics here. The coefficient of lift increases as the angle of attack increases until you stall. So in the next lesson we're going to talk about a stall, and it occurs when the angle of attack is too great to maintain the laminar airflow over the wing. The air above the wings becomes too turbulent to support the flight and the lift diminishes. So the bottom left of the graph here, it shows where an airfoil has a lower angle of attack, therefore a lower coefficient of lift. Moving from left to right along the x-axis, the angle of attack increases, so you follow the line, and you see the lift steadily increasing as the angle of attack increases until we get to the point where it stalls. So, in the diagram you see there, point out the bottom of the airfoil, out the bottom one, which is showing us the stalled condition where the coefficient of lift drops off too rapidly. The top airfoil has a smaller coefficient of lift because its angle of attack is lower, and it represents a point along the line prior to the stall. So the one on top's functioning as it should, but the one on bottom you can see is an example of it stalling out. All right, so we're talking about controlling the coefficient of lift. You know, pilots in general can't change the shape of the airfoil, so we have to adjust the angle of attack. So the only exception would be deployment of flaps for takeoff and landing, obviously. So the engineers are the ones who design the airfoil, the wings, everything. So they're the ones who can change the coefficient of lift by varying the shape and the thickness of the wing. So engineers have to consider how much lift is needed to make the aircraft fly, but must also consider, you know, the takeoffs, like drag, trade-offs, I'm sorry. So, all right, so this slide is trying to help you think about the effect of the coefficient of lift during the design process. So, you know, imagine your engineers tasked with designing an aircraft to go very fast. Is it a good strategy to design the wing with a great amount of camber? Will the camber generate significant lift without prohibitive trade-offs? And so these are the things that you need to be thinking about. So, and I'm sure you guys all just answered my question and said no. So the trade-offs will prevent the aircraft from operating effectively at high speeds. It is true that a wing with a great amount of camber will generate a lot of lift. However, it will also generate a lot of drag. If velocity is the goal, the wing would be generating more lift and thus more drag than desired. So as lift exceeds what is needed, it becomes difficult to keep the aircraft in a level condition. What's more likely to happen is that all the lift the wing will be producing would create so much drag that a pilot couldn't get the aircraft going fast enough in the first place. All right, so air density is a factor that can be considered a constant unless there's a change in the aircraft's position or altitude. The pilot has no control over the air density other than to place the aircraft in a different environment. As you guys recall from our third unit, air density decreases as the altitude increases and as the temperature increases. So remember, air density and altitude were inversely related. As altitude increases, an aircraft must fly faster to achieve the same amount of lift. Remember, less molecules? That's because of the lower air density at higher altitudes. All right, so we can't. All right, sorry, I had to pause it again. So, get in small groups. Wait, no, there's a pandemic. Don't get in small groups. Stay far away from everybody. So let's do this on our alone, because that's probably what's happening right now. You're alone and sad. So let's look at this scenario here. You and a friend are in Leadville, Colorado, but of course you're 6 feet apart, so you don't contract coronavirus. Over summer break for a hiking trip. The airport is at 9,934 feet in elevation. So, how will the high elevation affect the amount of lift your plane is going to produce? And then you're taking off in the middle of the day and it's 80 degrees, so it's pretty warm. So what's the temperature going to do as well? All right, I'm sure you're already saying the answer, but we understand, I think, that it's going to decrease the lift that the airplane can produce. So in order for the aircraft to have the required lift for takeoff, an aircraft departing at a high elevation airport where the air density is low must take off at a higher airspeed in order to make up for that lower density. This is one of the reasons why you need a longer takeoff at these higher altitude airports. And again, with higher altitudes and higher temperatures, that's going to create the higher density altitude, which means lower air density. So aircraft engines produce less power when there's less air density. So in this scenario, where the elevation and temperature are high, not only does the aircraft need to have more velocity to take off, but the pilot must also consider that the aircraft engine will produce less power. So this is the second reason why it will take longer to get off the runway. All right, guys, I know this PowerPoint's taking forever. I'm trying to get through it as fast as possible. All right, so velocity. So velocity is the factor that affects lift. Because velocity in the equation is squared, faster moving aircraft generate exponentially more lift. A pilot can affect velocity by changing the airspeed. This can be accomplished by adding or decreasing engine power, or initiating climb or descent. Because velocity is an exponential function of lift, doubling the velocity of the aircraft quadruples the amount of lift created, and the reverse is true for decreases in velocity. Sorry, didn't realize I didn't change the slide, so I'll leave that up just for a second. Next thing we're going to talk about is our surface area of our wings, our airfoil, how that helps lift. Alright, so I'm going to switch now. Maybe. There we go. So for smaller aircraft, the surface area of a wing remains relatively constant. And for the more advanced aircraft that have extendable flaps on the trailing edge of each wing and slats on the leading edge, that increase the wing's overall surface area when needed, particularly during takeoff and landing. Because of these flight control devices, larger and more complex aircraft can increase or decrease their lift by changing the surface area of their wings. All right, lift matrix. So again, in your packet, you're going to have this, the calculating lift activity. So I'm going to want you guys to fill this out. Take a picture of it, turn it in on Canvas. Again, I'll have links there. And again, if you need help, if you want to look over the PowerPoint, all that stuff is there for you. All right, so here's another one here. We've got the F-22 scenario. I can't remember if we've actually played around with the F-22s or not in the simulation. All right, so sorry, I got interrupted again. So using the lift equation, I want you guys to determine the speed of an F-22 fighter jet needs in order to take off at a given weight, air density, and angle of attack. Jeez.
Please pardon the interruption. Classified staff. You will check.
I also want you to determine whether or not the same jet can take off in a given scenario where the air density has decreased as the pilot prepares for a second sortie late in the hot afternoon in Vegas. So again, you have this activity. It's calculating lift, activity 2. So I just want you to complete that. And then take a picture of it, turn it in. All right, so I'm not going to worry about this one, but you can do it on your own. But I am not going to collect this activity for a grade, but it would definitely be beneficial for you to turn in, or I'm sorry, to do. All right. So here, you got 3 lift scenarios, and I just want you to do these problems and take a picture of it, turn it in. Again, if you have any questions about this stuff, shoot me a message on Canvas here, and I'll help you out in any way I can. If I need to call you to explain it, that's what I'll do. All right. So that is the end of our lesson. Have a good day. Stay healthy. Wash your hands. Stay 6 feet apart from people. Hopefully, Tyler's staying 6 feet away from his girlfriend so he doesn't get infected or he infect her.